Hey everyone, in this video we're going to be discussing linear equations in two variables, or more generally, uh, just equations in two variables, but we're going to start pretty simple here and talk about linear equations in two variables. And then, I guess the first thing we want to point out is the fact that we call these linear equations, and the reason why is because, well, the base here is line. We're going to be graphing lines, and this is sort of like the simplest representation of a relation between two variables here, okay? But yeah, let's go ahead and get started. You're going to notice here at the top of what I've written two different forms that are both lines, okay? But two different forms of an equation. And we're going to give these names, but starting with this one over here on the left. This has a name. You'll notice a few things about this, but the fact of the matter is the one thing that stands out is the fact that y is already isolated on the left-hand side. And then we have x over here on the right. X, of course, being to the first power here, would tell us that this is a first-degree polynomial, but that it's linear. But you're going to notice a couple other letters here, M and B, okay? This is referred to as the slope-intercept form of an equation, of a line, okay? And the reason why we refer to this as slope and intercept form is because of the fact that we see that M here and B represent both the slope and the y-intercept of this line respectively, okay? And another thing to point out here is this. The slope is m, but if we were to say look at an equation here, say like this first one here, you'll notice it's in slope-intercept form. It's pretty straightforward to see here that -2 is our slope and 1 is our y-intercept, and we'll talk about this one in just a second, but the fact of the matter is it would have been perfectly okay for us to write this as y equals, 1 minus 2x. But still, you have to know that this -2 is a slope, and the way we determine this is because it's the coefficient of our variable x here, okay? So anyways, this first form of the equation, y equals mx plus b, is slope-intercept form. You want to have that one memorized, okay? And then the other one over here, we're going to refer to this as standard form. And people always, they ask me, at least I have students, they say, how do I know if it's in standard or not? And the way I kind of always tell them to remember it is the fact that you'll notice here that both terms that have variables are located on the left-hand side of this equation. Or just, how about we just say anything that has a variable is on one side of the equation, while anything that doesn't have a variable is on the other. And, it's kind of convenient that we're using C here. It's very apropos because of the fact that C has no variable, therefore it is a constant term. It's always that number, okay? So let's go ahead and talk about just the basics of graphing these things without necessarily having to make an XY table and just kind of get the gist of it, okay? Starting with slope-intercept form. Okay, so example A here, and we can switch colors to kind of make sure we can see this here. Red tends to work pretty well, or you might call this pink, but anyways, the number one thing I want you to notice is this. Once we've already kind of identified that this is in slope-intercept form, it's a good habit to off to the side or somewhere else kind of write down necessarily what is the slope and what is the y-intercept. And in this instance, we can see that the slope is -2, and the y-intercept is 1. Okay, so now let's kind of talk about what these necessarily mean. Starting with the y-intercept. Okay, now the y-intercept, of course, is where this line or this graph would necessarily run into this entire y-axis right here, if you can see me moving my mouse or pen over it. But anyways, we want to find where it hits the y-axis. The neat thing, or the convenient thing about the y-axis, is that no matter what point you select off it, we know that the x value is 0. Okay, so therefore, what we can do is we can basically use this fact to back solve for this point or this y value. We're going to call it b for this y-intercept here. B is the letter we typically use. It's not a 6. But here's how we'll do it. We could necessarily take this x value of 0 and substitute it into the equation for x. And in this instance, you'd see that basically whatever you have in here for slope, whatever coefficient you would have, it would be a product between it and 0 when you find the y-intercept. And the nice thing about that is you could necessarily just ignore this entire term right here. And that's why we kind of just say automatically that, hey, this number, this constant term over here is our b term, is our y-intercept, because what we're necessarily saying is that x would be 0 if we're finding the y-intercept, okay? So, the fact of the matter here is that our y-intercept is 1. Okay, we've written this over here, but we'll go up 1 on the y-axis and we'll say, okay, so here's my y-intercept. And never a bad idea to label your points. So we say this is 0, -1 is our y-intercept, okay? Now we want to kind of analyze slope. Now, if you remember from algebra, and this is a lot of algebra right here, basic algebra, but We say slope is basically a ratio of how far our line rises as opposed to how far it runs, okay? So we usually interpret slope as a fraction or a ratio, but I think it would be appropriate now to say that -2 is not necessarily written in as explicitly as a fraction. So what we'll do is we'll go ahead and we'll put it over 1. Okay, so what we're saying here is that the top number is always our rise, and the bottom number, of course, many people know is our run. The run doesn't always have to be 1. We'll look at an example where it's not, but you'll notice here that the rise is negative, okay? This is kind of like a road map, but once we get our y-intercept, okay, we can necessarily proceed to it and then just follow our roadmap, which necessarily says from this we'll go down 2, okay, down 2 from this point and over 1. So if we went down 2 and over 1, we'd land here. And the neat thing about this is because this is linear, we know that this is a line. Every other point, if we were to go down 2 over 1, down 2 over 1, down 2 over 1 forever and ever and ever, all those points would necessarily land on this line full of solutions for this equation. But the fact of the matter is we only need 2 points to find the rest of the solutions on this line. Okay, so down 2 over 1. This is a graph of this equation right here. Pretty trivial, pretty straightforward. I do want you to notice one thing though. The fact of the matter is that whenever you have a negative slope, you can always expect that your line is going to be heading downhill. So this had negative slope, negative m, okay. But yeah, this is just a quick example of what this might look like, okay. So let's go ahead and move on to this next example here, and maybe it'd be easier if we switched colors on each example. That way we can kind of see things a little bit better. We'll go to this kind of pukey green, sorry to say it that way, but you're going to notice here we have another y equals equation. So already we can kind of safely assume that this is in slope-intercept form, but you might be saying to yourself, I don't see a something times x term here. I don't see a slope. So if you ever see y equals 3, we call this a constant function, okay? It's still linear, but we say constant. And the reason why is because, let's say we made a table of x and y values. It really wouldn't matter what you stuck in for x. Oops, that's just 0, it's neutral. -1, 0, 1, but y is constantly this 3, okay? And another way to think of this is we could put in that x term, we could say something times x, and it'd be entirely appropriate here to put in a 0. So this is going to be an example of where we have 0 for a slope. But again, good habit would be to, let's kind of explicitly state these. So our slope in this case is 0, or 0 over 1 if you will. And then our y-intercept is this constant term, we say 3. So just to graph this, it's pretty straightforward. We'll say we'll go up 3 on our y-axis here. We say there's that, good habit here. We'll label this 0, 3. Whenever you write a point in there, it's usually a good habit to label it. But using the fact that the slope is 0 here, now I'm starting at this point, but we say, okay, necessarily our rise would be 0. That means we're not going to proceed up or down from this point, but we are still going to run 1. Okay, so if I ran 1 from here, here'd be the next point. But now that we've got our 2 points, we can go ahead and play connect the dots here, and we say this is the line y equals 3, okay? And we should have labeled this up here, y equals -2x plus 1, sorry. But the fact of the matter is this, this is an example where we have 0 for a slope, okay? And I want to be really clear on this. 0 slope is not the same as no slope. And think about this. If you had a number line, if I put a number line up here and we say, okay, so 0, we usually write in the middle, but we have all the positives on the right and all the negatives on the left, and 0 is neutral. Think about it this way. With the negative slope, you saw up here that we have a line that's proceeding downhill, okay? And with a positive slope, of course, we'd have something that was proceeding uphill. But 0 always has to split the negatives and the positives. So looking up over here, you could not necessarily go from negative slope to a positive slope without having to pass through a slope of 0 first, okay? So we say a slope of 0 is a horizontal line. And the quick way to kind of recognize this is that there's just a lack of an x here, okay? There was no x, therefore a slope was 0, okay? So a horizontal line. And these are ones you really want to get used to. The funny thing is when I say y equals 3 to my students, they tend to write a vertical line because the y-axis is vertical, but it's kind of a backwards relationship, if you will. Okay? So now, let's go down to example C here. We'll blow through this one real quick here. You're going to notice that y is not isolated here. And you also notice that all the variables on one side, all the constants on the other, this is our standard form of this linear equation. And we're going to do just fine on this one. Now we can still find an x-intercept and a y-intercept. It's called the intercept method of graphing. But a lot of people get uncomfortable with the fact that y is not isolated. And the neat thing about that is, if it's not isolated, we always kind of have liberty to isolate it ourselves. So if we say we wanted to isolate y, the things we need to start targeting here are this 3x term and this coefficient of 2. But let's go ahead and kick this 3x term to the other side. So we'll subtract 3x from both sides, and if you've been a good algebra student, you know that, of course, we can't take 3x away from 6. They both don't have an x. They're not like terms. But we'd say, okay, so 2y would be equal to 6 minus 3x. I'm going to write negative 3x plus 6, just to kind of keep things consistent. And then we'll divide through everything now. That's the important thing, everything by 2. Okay, so we say y equals, now I'm going to divide this coefficient of x by 2, but we say negative 3 halves over 2. And you might be seeing already that that's going to be our slope. And then we have 6 over 2, plus 6 over 2 is 3. But here's where I'm going to list this. We say, okay, so our slope was negative 3 over 2. We're going to fall 3 and run 2, and our y-intercept is 3. We'll come back and visit this in just a minute. But let's go up 3. So, excuse me. Go up 3 here. We say, okay, so this hits the y-axis there. This is our y-intercept 0, comma 3. And from here, we're going to fall 3. So we're going to go down 3. 1, 2, 3, back down to the origin. Then we're going to run 2. Okay, so it's falling more than it's running here. But we say we'll drop in this other point. And we say, okay, so here's our line. And, you know, a lot of people probably know I'm using this example to be convenient. But we say this was the line 3x plus 2y was equal to 6. Or you could even write y equals negative 3x, 3 halves x plus 3. It's still the same thing, same set of solutions. But here's the thing about it. You notice here that the y-intercept was 3. And this was something we could have determined in the first place. Okay, so to do that, necessarily we, of course, would plug in 0 for x. And I want you to imagine this. Putting in a 0 for x over here necessarily would have caused this term to drop out of the original equation, which is convenient because if we can ignore that, what we're left with is 2y equals 6. You know, and to solve an equation like 2y equals 6, you know, when x is 0, we could just divide both sides by 2. And you see that we'd still get this y-intercept of 3. But the neat thing about this is, notice here that we had the x-intercept, okay? And to find an x-intercept, we'll just assume that y is 0 since all points on the x-axis have a y value of 0. If we would have plugged in 0 for y, which is something, by the way, we could have done, you know, say on this equation or the original equation, it would still work this out. But when something's in standard form, it's really convenient to just find the two intercepts, the x and y intercept, because plugging in 0 for terms is rather easy to evaluate. So plugging in a 0 for this y term now, 2 times 0 would be 0. That would drop out. Now we're left with 3x equals 6. And of course, if we had 3x equal to 6, you know, solving this for x, we would have found that x is 2, which is naturally what we see here, okay? So when we have something in standard form, know that you could just get away with finding 2 points, and those 2 points are most conveniently the intercepts, but you can also isolate y, excuse me. I will be a different video. And then this last equation up here. Now, kind of thinking back over here, we said that a horizontal line was necessarily any equation of the form y equals some constant c, okay, and it was horizontal. It was a y equals something without an x. Notice here that we have an x equals negative 4, and just to be, you know, really clear on this, when we say x equals negative 4, we're restricting x to being negative 4. That is, we always have to use an x value of negative 4. We say, so what could y be? And the nice thing about this is y can be whatever it wants. But I mean, if we were to graph these points here, you know, we say negative 4, comma 0, negative 4, comma 1, negative 4, comma 2. You're going to notice really quickly here that we have a vertical line, x equals 4. So the nice thing to remember here is, and you do want to remember this, but if you have x equals some constant, this is a vertical line, okay? And to be very specific here, we would say the slope, m, is undefined. And the reason behind this, you know, naturally rise over run, is the fact that if we were to write the rise on this line is always rising. You could say each time here we were rising 1, you know. And I can put a 1 up here for the sake of convenience, to be specific here, but it's, you know, some constant c on top. But the fact of the matter is it's not running. And of course we all know that if you divide by 0, you're going to have a problem. This is undefined, okay? Another way to say this is that there is no slope. Okay? So this is just kind of a quick overview of how you would graph some linear equations.